Ciao, here is a conversation with Niels Cranmer. Niels is a Ph.D. candidate at Princeton and is working on the interplay between astrophysics and AI. We start the conversation talking about symbolic regression. We talk about the history of the technique, starting from the 70s, going into the use of genetic programming in the early 2000s, and how his package symbolic regression.jl came to life. We discuss why he chose Julia to develop his package, and we talk about the relations between his package, sparse identification of nonlinear dynamics, SIND, the work done on deep symbolic regression at the Lawrence Livermore Lashell Laboratory, and also the work by Max Tegmark on Feynman AI. We touch on the work by Patrick Kidger and Chris Rockakis, and the relation between symbolic regression and neural network techniques. We also talk a bit about the choice of programming language used in software development, talking about Python and Julia in particular, and how Julia can relate both to Python and C++ in different ways. We then go into a weird topic, which is his use of LaTeX and overleaf. But from there we go into his way of approaching the study of programming languages and how to balance exploration and exploitation in software development, research, and life in general. From there we start talking about his research. We talk about the work did at Deepmind by Peter Battaglia. By the way, Niels joined Deepmind this year and is going to publish something later this year. So we talk about the work by Peter Battaglia on graph networks and their applicability in physics and dynamical systems also. We talk about the ability of these ideas to predict chaotic systems and to model them, so to predict dissolution in compact planetary systems. We touch on the use of it for deterministic chaos and turbulence, without going in detail though. We also talk about the ability of Bayesian neural networks to incorporate uncertainty, both epistemic and aleatoric. We talk about the differentiability of the model and also the interpretability of it coming from symbolic regression. And then what else? We talk about, at the end, the use of anomaly detection techniques coming from variational autoencoders to detect exotic supernovae. And we also discuss potential applicability of same ideas to study the space weather and the activity of the sun, to investigate critical transitions in the activity of the sun with important implications for space traffic management in low Earth orbit. We close the discussion on Lagrangian-Neural Networks and how they are perform better in some contexts related to Hamiltonian, while losing some of the power coming from the linear formulation, the symplectic geometry coming from Hamiltonian mechanics. Nevertheless, leveraging some symmetries and allowing one to model systems irrespective of the canonical formulation of the equations of motion. So I hope you enjoy it. Please follow Niels Cranmer's website, Twitter, GitHub, LinkedIn, I think. But yeah, he has a nice website, so I would suggest you to start from there. Link in the description. And yeah, I hope you enjoyed the episode. Please subscribe to my YouTube channel, follow me on Twitter and LinkedIn. And if you can support me on Patreon, I really appreciate it. And here's the conversation. We can start, and thank you very much for joining this conversation. I've been a fan of your work for a few years now, and I cannot do anything but start from symbolic regression, the work you've been doing on it. And so if you could maybe introduce people that don't know symbolic regression, if you could introduce the work of Schmidt-Lipson from 20 years ago now, something like that. And then from there, how Eureka became basically symbolic regression.jl in some sense.
Yeah, so I guess symbolic regression, it's a machine learning algorithm. So it's normally used for regression problems. So you want to fit some relationship between input variables and an output variable. But the difference between most machine learning algorithms, you fit some set of parameters inside some complex kind of highly parameterized model. In symbolic regression, you search for a symbolic equation that matches your data. Like maybe you search for like y equals x squared, and maybe that fits your data really well. So you're literally searching for equations, whereas in most machine learning methods, you have a fixed set of parameters, and you search for the best set of parameters such that your very flexible model fits your data set. So symbolic regression, from what I know, it goes back to someone called Patrick Langley, who did a lot of early work in so another way you could call symbolic regression is automatic equation discovery. So he had some very early methods, I think in like the late 70s,
right? Okay.
On this method called Bacon. And I think Bacon was I think it was kind of like a deterministic approach to search through all possible expressions and find one that fits your data. So he even had at that time like basic physics expressions, like the ideal gas law, and he actually showed you could find these. And then I think the first person to use genetic algorithms in this area maybe is Koza, and I think that was in the 90s.
90s, yeah.
And so he started applying genetic algorithms to this area. And then, of course, the really big paper that kind of popularized symbolic regression in the sciences is from Hod Lipson's group, who is at Cornell, is now at Columbia. So Hod Lipson, I think from 2007 to like 2010, his group had a series of papers, especially the one with Michael Schmidt, where they showed how you can use all of these evolutionary strategies to find expressions that match physical data very well. And they even showed at the time you could find like Lagrangians or Hamiltonians that fit your data very well. And it worked for like real numbers. Like it wasn't just integers, it was actually finding real numbers. And yeah, and so that produced the Eureka model. So Eureka, it kind of turned into a startup under this company called Newtonian.
Okay.
And then Newtonian was, I think a few years ago, bought out by Data Robot, which is this, I think it's like a machine learning web service. So Eureka is now part of that algorithm. And I think Eureka is still like the most powerful symbolic regression algorithm, but it's not open source and you have to pay for it. So I think most people don't tend to use it nowadays. Yeah.
Right. Okay. And so to go back, I wasn't aware of this work in the 70s. It wasn't, of course, genetic programming.
I wasn't either. I wasn't.
So it was basically brute forcing all the combinatorial space. And
so I don't know the specifics too well, but I think one of the early Bacon algorithms was closer to a brute force search. Right. I don't think it was a genetic algorithm, the first algorithm. I think it was more of a brute force strategy.
Right.
Yeah.
And so the starting point of symbolic regression.jl was Eureka.
Yeah. So I used to use Eureka, but it's open, it's closed source, it's proprietary. It costs like thousands of dollars. And now it's a web service. So like you can't even use it on your own computer.
Right.
But what I really want, and I think what other people really want, is something I can plug into my Python pipeline and kind of use in an open source way, and maybe put it on my compute cluster and just use it like any other tool. So there were some tools like GP-Learn is one tool that I had looked at, but I found that GP-Learn and other tools, they were really not as powerful as Eureka at all. And I couldn't actually use them in my research because they're just not good enough at finding expressions. So I got frustrated, and then I finally just decided to write my own because I just wanted a tool I could use. And so at the time I was kind of like, I was thinking about what I wanted to write it in, because it, like, so if you're writing a machine learning pipeline, there's a lot of existing tools for machine learning, like, neural networks. If you're writing a neural network tool, there's a lot of neural network tools that can let you write like a very fast model. But it's not true for genetic algorithms. There's not a lot of good tools available. So most people have to write it from scratch. So at the time I was thinking like maybe C++, but I had read about Julia, which is it's a relatively new programming language. And
this was, sorry, 2018.
This was 2020. This is 2020.
Okay.
Yeah.
Okay.
And yeah, so I read about Julia a bit. I don't know. I was kind of like a big Julia skeptic for a while, which is funny because like now I am a huge Julia supporter, but I was kind of like an anti-Julia fanboy. Like I'm all Python, C++.
Yeah. Okay.
Like why do we need another Python? But then I started looking through benchmarks, like various benchmarks, and one of the benchmarks was for tree search codes. So a tree search code is like if you have tree structured data, what's the fastest language for building codes that traverse these trees? And I think it was like C++, Rust, and Julia was up there. It was like a really fast implementation. And I looked at the code, and the code was really, really simple. And I think high-level languages are always best for research. I think C++ and maybe Rust are good if you know exactly what you want to build. But at the time, I didn't really know what I wanted to put in this algorithm. And high-level languages let you make changes quickly. So I thought I want the fastest high-level language for writing a symbolic regression code, so I chose Julia. And so that's how I started writing this thing. And now it's like mixed Python Julia. So it's got the Python side for like easy interfacing, because most people use Python. So it's got the Python side and then the Julia side for speed.
Okay, so the core runs in Julia, but
yeah,
it's interface. It's like having, I don't know, C++ and then binding it with bybinds or something
exactly.
like that to Python.
Yeah, I definitely, so most people think of Julia as like a Python replacement, but I think of Julia as like a C++ replacement.
Right.
Because it's got the same speed. It's got the same speeds as C, but it's high level. And so it has the potential to be both the front end and the back end. So it has the potential to completely replace Python and C++. But I think at the moment, the Python ecosystem is so massive that you really only want to exploit Julia for the back end right now.
Right. But do you still see a space for C++?
I think, yeah, I definitely think there's some things that C++ is, I mean, C++ is so mature, and for many things, I think C++ is better, especially like as a systems language. And I even think Rust will probably be the next C++ rather than Julia. But I think for high performance computing in research, like where you're building software quickly and maybe you don't need to use it for like if you're writing someone in C++, you want it to be reliable for like 2 decades.
Right.
But if you're writing a research code, you just want it to be fast and you want it now, and you want to like make something and change it. I think Julia is really nice for that. I think in the future, Rust is going to be, I think Rust will be the replacement for like systems level languages. Like if you're building like an operating system, I think Rust is a really good option. I'm not sure if Julia would ever fill that area, but I think Julia is perfect for like high performance scientific computing.
And do you think, I mean, basically I had a similar experience in looking for benchmarks for numerical integration of both deterministic and stochastic differential equations. And and so I had this tension. Okay, Python has so many libraries, so I cannot leave it. But Julia kills it. I mean, it's so fast. And someone pointed to me. I mean, yeah, you can have Numba, you can have JAX to speed up. Numerical integration in Python.
Yeah, I think if you want a standard kind of like if you want to do like matrix multiplications, like normal deep learning stuff, I think Python's actually the way to go still, because there's so many frameworks, there's so many machine learning frameworks that people have optimized to hell the C++ backend. So you don't actually need to use Julia. Like you can use pure Python.
Yeah.
And someone's already written PyTorch and poured like all of this industry funding into it. But I think if you want to write, if you need to write something yourself in C++, I think it's better to use Julia. Yeah, so for symbolic regression.jl, it needs a tree-based machine learning algorithm, and PyTorch and JAX, they're not good for that kind of approach. Like they're for fixed size matrix multiplication and differentiation, but not really for like tree traversal codes.
Right.
So I think if you have if you have something that needs like a custom structure, then I think you want to write it yourself in Julia.
Interesting. Yeah. This is, let's say, cutting close to the bone, because I've been working on symbolic regression using Python, and using Deep. I don't know if you know the library, but it's genetic programming, and it's Deep. D-E-A-P.
Yeah, I think that one's used in GP-Learn, right?
Probably yes. But yeah, it's really slow, and definitely worth studying a bit what your package does. And but yeah, maybe to discuss a bit more about the ecosystem of this field. I'm a big fan of Cindy, sparse identification of nonlinear dynamics, and actually what we're doing now. And I saw you did the same. I don't know if you yourself worked on it, but with I don't remember the name. This PhD student that just graduated from Oxford. That I don't know.
Patrick Kidder.
Probably yes.
Yeah.
In his appendix said something about combining symbolic regression with Cindy, and I had done it in 2020, but now we're actually writing a library for it. And we wanted to go with Deep because I had experience with it. We had already the code, but it's so slow that maybe it's time to jump on your truck or your wagon. But yeah, so if you could discuss a bit. Also, I'm aware of deep symbolic regression by someone at the Lawrence Livermore National Laboratory.
Yeah.
Then there's Max Tegmark with Feynman AI. So if you could give, I don't know, an overview of what you see around. I mean, from my perspective, I see these people, including yourself. Is there someone I'm missing? Is there a hierarchy of, I don't know, preference for some things and for others something else?
Yeah, so I think, so all of those algorithms that you listed have different search spaces. And I think if you want to use symbolic regression, the search space is really important. So like if you want to search for, if you want a dictionary-based symbolic regression code, like you know your basis functions. So you know your differential equation is like a polynomial. That's where Cindy fits in really nicely. If you don't know your basis functions, then that's where you need kind of like a genetic algorithm-based approach, because that lets you find kind of nested hierarchical expressions. And I think, so Patrick Kidger and I, so this hasn't been published yet, but it's in his thesis. It's basically like we train a neural differential equation on some problem, and then you try to extract the acceleration from it using like a genetic algorithm based approach.
Oh, okay.
So
because
it's
been
another
working
way
on neural differential equation like the DFQ, the group with Julia. I mean, is there a similarity also there? Different? I mean, I know there's a difference.
I think he wrote his code in JAX.
Right.
So he has a package called Diffrax that just came out like a week ago. So he wrote his in JAX. I'm not sure if he uses the Julia side, but he uses the Python front end of symbolic regression, which is called or symbolic regression.jl, which is called Pyser. And so he basically has a demo of it kind of like fitting into Pyser to find like an arbitrary differential equation. So the other software you mentioned, so deep symbolic regression. So that's a cool approach. I think it works basically. So I think they have a neural network that's like a generator of equations. Like it's basically like generating different equations. And then they compute the loss of the generated equation, and they back propagate the loss, and they kind of like update the generator. And I haven't played around with it too much. I'm not sure if it works for real numbers, but it might work for real numbers. I'm not sure. I don't know. I still need to play around with that approach. The other paper you mentioned is AI Feynman. So AI Feynman doesn't work with real numbers. So I can't use it in my research because if you are finding a new scientific expression, you don't know the constants ahead of time. So if you're just using known constants to kind of rediscover an equation, that's, well, like I basically can't use that. Like I consider myself more of a user of symbolic regression than a developer, but I became a developer because like nothing, I can't really use anything. But yeah, AI Feynman is really cool, and it has different, it has like symmetry discovery techniques inside it, which is cool. Like I think they use a neural network to discover the symmetry between two variables. Like maybe two variables are like translationally equivariant, so then they can just like use that expression in the search. So it's a really cool approach, but I can't use it at all because it just finds like integers in the expressions. But I need real numbers.
Could you explain, maybe before we keep on this, how does symbolic regression.jl look for real numbers? Because when I started playing with it, basically I had a nested optimization in which I had this combinatory one outside, and then for each individual, I was optimizing the nonlinear parameters, which was a nightmare computationally.
The way Pyser finds real numbers is, so there's a main like evolutionary loop. So there's different genetic operators, and you basically randomly choose a genetic operator, apply it, randomly choose a different one, apply it. One of the genetic operators is called Mutate Constant, and it will take a random constant in the expression and change it. And the way it changes it is it will either increase it by between 0 to 50% or decrease it by 0 to 50%. Or it will randomly flip the sign. So you can explore, that basically lets you explore the entire real line, because you can kind of keep like, maybe you keep increasing it, the constant gets bigger and bigger and bigger, or you keep decreasing it. So that's part of the evolutionary loop. And that's okay. Like that kind of works in a lot of cases. It lets you explore different real constants. But the other important part of Pyser is it uses traditional optimization on the constants as well. So after doing a certain number of cycles, like after doing maybe like 100 generations of different expressions, it will do like explicit optimization of the constants
without touching
so it fixes the expressions. And then it does like BFGS optimization. So that's like traditional constant optimization. And that
it starts again from this optimized tree.
Yeah, exactly. Yeah. And yeah, so that tends to help a lot with the constant optimization. And the other thing is it does crossover mutations as well. So it might take two expressions and then randomly move one sub-expression of the first one into the other one, and randomly move the replace sub-expression into the first one. And that can move constants too. Yeah.
Yeah, interesting. Yeah, I read, I think in early 2020, this idea of having like a Gaussian distribution from which you sample, and the mean is the constant you have now, and then I don't know, you decrease the variance with the generations, let's say.
Yeah. I guess PySer kind of works that way.
But yeah,
I still need to write the methods paper. The methods paper is like, I think it's like 2 weeks away, and then I'll finally post it.
Will be on the archive.
Yeah.
Great. Looking forward to it. I have a ton of questions. I guess cool. This is a specific one, but I guess it also goes back to the choice of the programming language, and also how to approach learning a new language. And the question is, I see a lot of tweets from yourself about overleaf. I see you know many functionalities of LaTeX, and I'm not only unaware of them, but I am also unaware of the process that allows you to discover them and to leverage them. Because and I would say this applies for me in many programming languages. I learn by using it, and then I don't know, I get stuck in this local minimum in which I do over and over the same things, the same approach, which are maybe a bit far-fetched. But you seem to explore you seem to have an exploratory part in learning programming languages. I mean, at least in overleaf.
Yeah, it's a good point. I've never actually thought about this, but yeah, I guess I do that.
How
a
does
lot.
it
Like
happen?
most people use overleaf and they never find like these random obscure features.
Yeah, I mean, I had to define a function that removed the italic from inside the expression. I did it by hand, and then one day you posted something about, okay, there's this function that does it, which is already existing there. I think the example was this one, but I may be wrong. But yeah, the idea is this. So how did you arrive there? I know it's a weird question because for you it's natural. But...
No, it's a really interesting question, because people have like I'm really my hidden talent is finding really obscure features of like software that are like useful but not well documented. I'm trying to think of how I did that for overleaf. I think most of the time I just Google, like I just get really pissed off that I can't do something, and I'll just Google for like 2 hours until I find this obscure functionality that that would be useful for this. Like, I guess I spend a lot of time, probably too much time, optimizing my workflow. Like actually optimizing like what Vim plugins I use, like finding new Vim plugins. I think I spend maybe too much time on that. And it's the same for like overleaf or programming languages. Like overleaf, I don't know, one day I just really wanted to use Latex Diff inside overleaf. So if you don't know what Latex Diff is, it's basically like you have the old version, the old LaTeX version of a document and the new one. And Latex Diff will generate a new text document that has the actual text that you've deleted, like highlighted in red. And it doesn't do that on the text itself. It actually renders that in a PDF. So it will render a new PDF with like underlined changes, which is really useful. Like if you're co-authoring a paper, you could just send the Latex Diff PDF over, and you're like, I made these changes.
Right.
So yeah, so one day, I just got really, I just really wanted to do that inside overleaf. I don't know why. I just really wanted to do that inside overleaf. And I think I spent like a few hours trying to figure out how you could do this. And I literally just Google a lot. Like I don't actually read through the documentation of overleaf, like line by line. I just Google and Google and Google until I find how you can do this. And I think, Yeah, I was just like I think I first searched like how to do LaTeX diff and overleaf, and then there's nothing. And then I searched like how to run command in overleaf, or how to like change the pre-processing in overleaf.
Mm-hmm.
And then there were some articles on like using LaTeX make RC, which
Mm-hmm.
is like the build commands for overleaf. And it turns out you can actually change these inside overleaf.
Mm-hmm.
And then, so I don't think anybody had done this with LaTeX diff yet, but you
Mm-hmm.
could take the pre-processing stage and just change the pre-processing stage to actually run LaTeX diff.
Mm-hmm. Mm-hmm.
So I don't know if, like, I don't think it's actually set up to do that, but it turns out you could do that. But I think, yeah, it's interesting. I've never thought about that, but I am my hidden talent is finding like random obscure things in software that are useful. And I think my strategy is just get really obsessive about one thing I want to do, even if there's not really any like well documented way to do it, and I'll
Mm-hmm.
just kind of Google things until I find the way.
Right. So like
Yeah.
you never, I mean, because I've never met someone, I mean, I'm not a software engineer, but I've never met someone actually studying books about software. It's all
Right.
Google,
Yeah.
also in my experience.
Yeah.
So I wanted to know if for you it was different.
Yeah, I guess it is like Google. Yeah, it's mostly Google. Maybe I'm just really stubborn. I don't know. Like I just want to
Maybe
do
you dig
something,
more.
and I just like obsessively Google it until I get the way, and then I like find some new feature that nobody knows about.
Yeah. Yeah.
I don't know. Yeah.
Yeah. Yeah. I mean, I guess this is opening an even bigger question about how do you balance research with applications? How much time? I mean, yeah, being a researcher, okay, you have this sphere, but let's say if you consider society as a whole body, how much time should be spent on inhabiting what you already have and getting the implications of that and going outside. I may have a stupid example on this, but when I was playing Minecraft when I was younger, I never spent time outside the cave looking for diamonds. I was never actually enjoying the diamond. I like the process of digging, which is why I guess I like research. But of course, when another person could say, yeah, I have this place, this house, I like it, I have sheep, and I don't care about digging. So how do you I don't even know what the question is, but what's your balance? Maybe that's the question.
Of like exploration versus
exploitation. Yes.
Okay. Yeah, that's a good question. So to be honest with you, I have like, this is probably one of the weirdest things I do, but I literally wrote my own time management software, which is like crazy. But I have this Python package that I wrote. It's a private Python package because it like there's a bunch of like personalized stuff in it. But so I actually have a formula for how much time to spend on like each task.
Okay.
And the way the way it calculates how to do something is like, so I have this database. It's literally just like a CSV file. And it represents like, what is the task, how long do I expect it to take, and when is it due, and then is this a hard deadline or a soft deadline.
Okay.
So like if a paper's due, then that's like a hard deadline. And then I have another column which is how much I want to do the task.
Okay.
And the funny thing is like the score actually inversely weights how much I want to do the task. So if I want to do the task more, it'll actually like reduce the priority, because it's kind of like I already have this bias that I want to do this task. So it'll give me tasks I don't want to do first, basically.
Okay.
But so the way it works is it computes so like how far in the future is the deadline, how many hours do I need to work on it, and then it will look at how many hours I need to spend per day to reach that goal. And so the task that has the most hours per day to reach that goal. So say like a paper's due tomorrow, and I think I have like 10 hours to do, then obviously that task is going to be at the top because it's like I have to work on it 10 hours per day. And then it will also weight this by how much I think the task is important and how, and then also like how much I want to do it. And that'll be an inverse weighting. Yeah, so it sounds a bit ridiculous, but it's actually helped me a lot because like sometimes it's just really hard to figure out like what you should do on a given day. Like there's just maybe you have like a to-do list and there's like a ton of things that you have to do, but you don't know which one you should do first. And I found it's really helpful to have something like this where you can say, oh, this task I have to work on this many hours today to finish it by the deadline. So I should work on that first. So I actually have this script that's called like task scheduler sample, and it will generate a task to do for like 1 hour. And I just like hit sample and it'll generate like, okay, do this for 1 hour, do this for 1 hour.
So it's an hourly.
Yeah. Well, so usually what I do is just generate like maybe 5 times at the beginning of the day. I'll just sample it 5 times and that'll be like, I need to do this today.
Morning. Oh no. Okay.
So so I guess to conclude, like I don't really choose what I do myself. I literally have like an equation to do it. I don't know if it's like, it's probably not optimized, but it's just nice to have a quantitative way to go about this. It just makes me feel better about doing this because it's actually it's quantified. Like I have to do this today. So I found that that's helped me a bit.
Break the rules, let's say?
Yeah, I break the rules a lot.
Okay.
Like if I think the task manager has kind of not weighted something highly enough, or maybe I forgot to put something in the task manager and I'm like, oh, I forgot I have to do this tomorrow, then I'll just add it manually. But it is nice to kind of have this task manager that I can always sample and see what I have to work on.
And does it stop you from, because basically I use Google Calendar and it doesn't satisfy me. So if you could share the script, it would be great, or a simplified version. I don't know. I use Google Calendar, and I wanted a few months back to not allow it to give it the power not to allow me to overlap things to do. Yeah, because I tend to overestimate my time, my ability, my efficiency. I don't know. And so does this system stop you from overeating?
So there's one command that will tell you in 1 week the amount of time that you have to spend on your tasks is like way higher than the amount of hours in the week. And then that's a good indicator, like, oh, okay, I'm way overbooked, so I have to cancel.
I need to cancel some.
Yeah. So I find that really helpful. And I guess so I used to use Google Calendar too, and the thing I don't like about it is if you have one task that will take you like 50 hours to complete, but it's like 2 months away, versus another task that is next week and it takes like 1 hour, then what do you work on? Like, so if you just look at the calendar, you'll see the 1 hour thing 1 week away. But if you look at this task scheduler, it'll actually make that 50-hour task appear higher just because you have to spend more hours to it, which is really what I want. Like I want something that has a longer time horizon. So if something is going to take a really long time, but it's in the future, then I'm still going to work on it, basically.
Interesting.
Yeah, and actually, like earlier versions of the software, like I started using this in undergrad to help manage like assignments, because I never knew what assignment to work on. But I literally was using Eureka, like the symbolic regression software Eureka, to create the formula for task prioritization.
Okay.
Okay, so the way it worked is I would write out like all these tasks, like maybe 10 tasks, and then I would read through the stats manually. Like this task is due in 2 weeks and it has this many hours.
Okay.
And I would write down a manual score for each task based on my own reading of them. And then basically I used Eureka to find like a simple formula that reproduces the score I want. And so that formula is the basis of the scheduler. So it's kind of like it's informed by what I want it to show. But I didn't really need to engineer it myself. Like I just used symbolic regression. Yeah, I know it's crazy, but it helps me.
Yeah.
Yeah.
No, I think this is the best way to do research, like to apply to toy cases, which are live, but
yeah. The other thing is, so I don't know why, but Google Calendar, it will show you 1 month away, but in research, like research is a marathon, it's not a sprint, and you kind of need a much longer time horizon for tasks. So I have this my task scheduler will generate a calendar that's like 4 months ahead, so I can see every day 4 months ahead, and I can see, oh, I have to do this thing 4 months in the future. So it kind of helps me I don't know, plan for long time horizon events.
This is
I mean, I'm still bad at following the task scheduler, but it is helpful, like especially if I'm in a crunch time, then I can just rely on it to give me tasks.
Definitely. Once again, I hope you can share it, because sounds like, I mean, mainly because of this delayed gratification thing.
I might have a open source version. Let me see. I think so my personal version actually contains the tasks themselves, but I think I made a public one. It's called HTM, Human Task Manager. Oh yeah, so there's a GIF demo actually on the on the README.
Great.
It's like, what is the task? Estimated hours. What date is it due? And the date, it uses this Python date parser, so you can put in like Friday and it'll figure out what date it is, or you can put in like February 23rd and it'll figure out the date. And then you can say, is it a hard deadline?
So you're not using any calendar besides, I mean, are you using something else?
So I use both Google Calendar and this.
Okay.
I think, well, Google Calendar is nicer for I guess if I don't know. I don't really know. I guess, I use Google Calendar for organizing meetings, and I put deadlines both in this and Google Calendar, because Google Calendar will actually send you like an email, which I like. Yeah.
Let me save this. So HTM. I guess I can put the link in the description. Really interesting. Because I was saying, you said it brilliantly. Research is a marathon, and I mean, I would argue life is a marathon, and not a sprint. I mean, there are moments in which you have to sprint, but so having something that reminds you that you should avoid shortcuts, let's say, is probably
and it's nice to have because I guess like the optimization function that my brain is always trying to solve is very short term. Like I think we're short term creatures in general. Like we always want to get short term rewards, and it's hard to convince ourselves to think about very long term goals. So it's nice to have something like this to kind of like ping you about, you have this task due way in the future, maybe spend an hour today on it.
Brilliant. I guess we can start talking. I mean, this was really deep, I think, in many ways, but we haven't talked about your research. So I don't know, maybe we could start by talking about the fact that you worked with Deepmind at Deepmind. I don't know. You joined them recently, and can you explain what you did and how this relates to what you did before?
So I'm So it's actually not published yet, and they have a very strict non-disclosure agreement.
Mm-hmm.
So I'm literally not allowed to say a word about it. I can say
when is this coming out?
It'll come out this year.
Okay.
Hopefully before the summer.
Okay.
But I think the main result might be after the summer. But it is in the realm of graph networks and physics.
Mm-hmm. So you work with Peter Battaglia, right?
Yep.
Interesting. Yeah. And could you explain? I mean, I had never, to be honest, I read your papers often since, as I told you, when I started my PhD in 2019.
Oh, that's cool.
But I've never, when something, you feel something is resonating, and then you start digging. I saw you at value, but I never. What's the past of digging? I never dug into the references, let's say, and just preparing this conversation, I read about this. It seems like a core work for you is learning symbolic physics with graph networks.
Yeah, definitely.
And I think you're referencing some work by Peter Battaglia there that's referenced often in your works. So maybe you talk through the ideas described there?
Yeah. So I guess the way I'll start is most deep learning is built for vectors and images and sequences. So like if you have vector data, like you have a list of columns and you want to predict another column, maybe you use like a multi-layer perceptron. If you have an image, then you use a convolutional neural network. If you have a sequence, maybe you use an LSTM or a transformer. But there's not much available for, well, there wasn't much available for like data with unusual type of structure, like maybe a graph. Like there wasn't any deep learning architectures available for graphs. So like a graph is you have different nodes and maybe you have edges between some of the nodes. So for a long time, there wasn't really any type of deep learning architecture to work with these. So that's where graph neural networks come in. A graph neural network will take a graph and output another graph. So it might take these nodes and edges and output these nodes and these edges. So this type of architecture is really useful for physics because many things in the physical world are well represented by a graph. So like if you look around your room, there's different objects and you could think of each object as a different node in a graph. And maybe the edge between two nodes is like the physical connection between two objects. Like maybe this book on my desk, like that's a node in the graph describing my room. And when I put it on the desk, there's like an edge between the book and the desk. So the natural world is very well described by graphs. And especially even if you look very at the micro level of the world, there's particles, and particles, you can stick them in a graph very easily. So if you tried to embed particles in a normal deep learning model, you would have to kind of embed them in a grid or something, which is not, it doesn't really represent the natural structure of the world. Whereas a graph network, you represent things as graphs, and it's very well suited to the natural world. And this is even true for very large scales. Like a galaxy could be a node in a graph, and maybe other nearby galaxies are connected with edges because they influence each other. So graph networks are really nice for processing things about the natural world. So in one of those, so I guess the way it started was Peter Battaglia gave a presentation on graph networks. He basically said what I'm saying right now. And he showed some demos of graph networks on particle physics problems. And one of the cool things was you could train a graph network on 6 particles and it would generalize very well to like 8 particles or like 10 particles. It would, and if you tried to do that with like a regular neural network, maybe take like a convolutional network and generalize to like a larger system, it doesn't really work that well. But this graph network, it really worked nicely. So at the time I basically, like I thought, okay, it looks like this graph network actually understands physics. Like it actually learned the physics because it generalizes that well. Like it has to, and so the idea was like, it has to have physics inside of it. Like somewhere in this graph network, there's like Newton's law of gravity. So the first project in this area was trying to figure out where the physics is in the graph network, and actually like prod different parts of it and see like where's the physics. And so eventually we found out, okay, the physics is in the edge function of the graph network. Like when you pass messages in a graph network, like it's basically like two nodes in this, there's an edge between the nodes. So a message might be from one node to the other, or this node to that node. And so if you think about it, this is kind of related to normal physics, like you pass forces between particles. So what we try to do is see, can we distill the force law learned by that edge function? Like if you train a graph network, can you actually distill the force law learned by the graph network? And that's like extracting the physical knowledge learned by the model. So the first thing we did was we fit the graph network on like some spring data. Like you have a bunch of particles connected by springs, and you literally just fit the true spring force law to the to the edge function learned by the model. So that the edge function is a mapping from this particle and this particle to some long message vector. So it's like it takes particle A, particle B, and there's a function to this vector that is the message between them. It's maybe like 100 dimensions. And so what we did to start is say, like, this is a 3D system. The force law should be three-dimensional. So the first thing we did was just say, okay, the message function, let's make it 3 dimensions, because that's like the same number of dimensions as the force law. When you do that, then you can look at like each component of the message and see it perfectly corresponds to a rotation of the true force law. So if you train this on like different systems, you can fit the original force law to the message function learned by the graph network. So that first paper, I think, yeah, like learning symbolic physics from graph networks or something. Like you could show how to actually prove this graph network has learned physics. So that was the first paper. The second paper, we said, okay, you know how like we're reducing the dimension to like 3?
And you do this
know
with
it's 3 dimensions?
autoencoders or something like that?
Sorry?
Do you compress it with autoencoders? Is this
So basically, like what we do, instead of like forcing it to 3 dimensions, we let it be 100 dimensions. But then we give the network like chocolate. We give it chocolate if it can use fewer dimensions. Like we
Right.
reward it.
Yep.
So like if the network uses like only 2 dimensions, it gets like a bar of chocolate. Like in the loss function, I mean.
Yeah.
And so what happens is the network will automatically reduce itself to the required number of dimensions, like the minimum number of dimensions. So if it's like a 3D system, it will end up using 3 dimensions in the message function. So what we found is like you can actually teach a network to recover like a force law without enforcing it. Like the network will just discover it if you reward the network for sparsity. Like you say, okay, if this network, if it uses as few dimensions as possible, it gets a reward. So the network will actually try to reduce itself. And then the second step is to, like, if you don't know the force law and you want to find what force law has the network learned, then you can use symbolic regression. So you can use symbolic regression and extract the force law, basically. So like you have particle A, particle B, and you predict these three numbers. And so that relationship, you approximate it with symbolic regression. So that's how we started like finding force laws without knowing them, using graph networks. And the reason like this is really it's kind of interesting is like if you tried to do this with pure symbolic regression, like you wouldn't know how many dimensions there are in that message space. But because this model is differentiable, it will learn the number of dimensions.
Right.
And then we can do symbolic regression after. So the basic premise is like deep learning is easy, symbolic regression is hard. So first use symbolic regression, or first use deep learning to like solve the problem, and then use symbolic regression as a post-processing step to figure out what the neural network has learned, because symbolic regression is hard. So it's like the neural network kind of breaks the problem into smaller pieces.
And the idea, I mean, I remember you underlined somewhere that the model is differentiable, as you did now in some paper. Yes. That's because it's a deep learning, it's a neural network.
Yeah.
Yeah. Right.
So so most approaches to deep learning symbolic regression, the deep learning actually does the symbolic regression for you. But the way we do it is the symbolic regression is like a interpretation step of this neural network. Like you take any neural network and you try to interpret it with a symbolic regression.
Yeah. Great. And I saw you applied this idea. I'm not sure if it's the same, but to predict the dissolution, for example, of planetary systems. Maybe that's a different.
Yeah. So that one we didn't use symbolic regression yet, but I think it would be really interesting. So I think for a future project, we want to use symbolic regression there.
So you want to basically have a Bayesian inference coming from a Bayesian neural network.
Yeah. So that paper is we have a planetary system, and you try to predict when the system goes unstable. So maybe like a planet gets ejected, or there's like a collision between two planets, and it's really hard to predict that because it's a chaotic system. So like if you move a planet by 1 centimeter, the planetary system could like last 1 billion years longer before it goes unstable. So it's extremely chaotic, nonlinear. The reason a Bayesian neural network is nice because it gives you error bars at the end. So you don't really need to worry about the exact prediction. You just have error bars.
Yeah. And I don't know if you saw, I mean, that's really interesting. I mean, in general, the use of AI for dealing with deterministic chaos. I could read something about applied to finance, but at least discussed in the context of finance, but basically showing that you could use machine learning to predict the behavior of a chaotic system much more than its Lyapunov time, which is basically the time after which chaoticity plays a big role. Did you see something like this? Also, I'm thinking about the work by, for example, among others, Jacques Lascar on the stability of the solar system, on the chaoticity of the solar system, actually. Yeah. Did you look into something like this?
Yeah, so I guess like in planetary systems in general, the really interesting thing is even though it is so chaotic and hard to predict exactly, you can still establish like a bound for quantities. Like even though it is completely chaotic, you know things about the final state. You know the final state is going to have the same energy, right? You know the final state is going to have the same angular momentum. And you can also figure out the point at which it goes unstable is going to fall within some bounds. Like even though you can't predict the exact point, like that's the definition of chaos. You can't predict the exact point, but you can predict where it will fall, like where that instability time will fall. And I think that's true of many chaotic systems. Like even though it's impossible to predict the exact point, you can still approximately infer where it will happen. Yeah.
Interesting. And this approach allows you to incorporate both uncertainty coming from aleatoric, both aleatoric and epistemic uncertainty, right?
Right.
Can you explain how? I mean, I guess you already did, but could you maybe describe the difference in this context? And
right. So Alliatoric uncertainty it's kind of like your data uncertainty or the intrinsic uncertainty. So like your data, maybe you've observed it with some noise, like your detector has some noise. Or in this case, like when you simulate a system to the end, the instability time, since it's chaotic, like it's not really, it kind of falls within some airbound. And you could think of that as the Alliatoric uncertainty. Like it's the intrinsic noise in the measurement. Whereas epistemic uncertainty is the model uncertainty. So if you make a prediction that is out of your training distribution, for instance, the uncertainty on that prediction is the epistemic uncertainty. So Bayesian neural networks do both. A lot of neural networks are just point predictions, like you predict a single point. But in science, we care about both kinds of uncertainties. We want epistemic uncertainties to know how accurate our model is in some interval. And we also have measurement uncertainty. So we need to incorporate that as well.
Yeah. Great. Yeah. And a separate question about a different work, which is anomaly detection for multivariate time series of exotic supernovae. So maybe could you, my interest in this comes from the fact that I've been studying space weather and the activity of the sun. And basically you have these events, like you have these events in the solar activity, like coronal mass ejection. And these are interesting for me because they have influence on the atmospheric density, which has influence on the behavior of satellites in low Earth orbit. So in the context of space traffic management, you're interested in characterizing the motion of the spacecraft to avoid collisions. And to do that, you need to describe the evolution of the thermospheric density. And to do that, you need to, in some sense, understand what the sun is doing.
So do you actually use like anomaly detection?
I don't think people use that.
Like anomalous. Okay.
I know people using machine learning. Time series analysis, but I've never seen people do anomaly detection on that. What we're doing now is actually consider the sun activity as a stochastic dynamic system and try to do probabilistic predictions. But I guess that's one half of the story, because for anomalies, it's a different game, I would say, and it's where things get interesting for the sun, because that's when things get tricky from a space traffic management perspective. So this is, I would say, more of a research proposal than a question. But maybe could you explain anomaly detection, variation autoencoders, and if you see them fitting in this perspective of the study of this activity?
Yeah. So for this application, I guess so. A lot of astronomy research, I guess, especially in transient research. So a transient in astronomy is a star that, I guess, has some intermittent behavior, or it's not really like a stable source of light. It is it has some variable behavior. So we call these transients. And so in this kind of research, what you're really interested in is finding a star that is unusual and then trying to explain it.
Mm-hmm.
So for instance, I don't know if you've seen these things called fast radio bursts.
Mm-hmm.
So it is a very fast.
Are this gamma ray, right?
Burst of, so there's gamma ray bursts and there's fast radio bursts.
Okay.
I think yeah, I don't know if there's a connection. There might be in some cases, I'm not sure. But basically, like a fast radio burst is a very short duration burst of radio emissions.
Oh, okay.
And so people have been looking at, like, we don't have a model for these. So can we develop a model that explains these? And we try to figure out what kind of source is producing these bursts. Mm-hmm. So a lot of astronomy research is like that. Like you make an observation and then you try to explain it with physics. And you keep going through this process, refining our models, or if you find a new observation that you don't know, you try to explain that with a new model. Mm-hmm. So in this vein of research, you are trying to find light sources that are weird, basically. Mm-hmm. Like you try to find a star that does something you don't expect, because then you can use this as like an object to do research on and try to figure out what is it doing, what models can we use to explain this. So in this particular paper, we were looking at can we use anomaly detection methods from machine learning to try to find unusual stars that we could. So in astronomy, there's a thing called a survey. So a survey is basically you have a telescope and it's monitoring the sky all day, all the time. Then there's smaller telescopes, which might be directed at a single star to kind of take detailed measurements of that star. So the pipeline is you have this survey always scanning the sky. Maybe the survey it finds this weird star and it's doing some weird bursting thing. Then it will send a signal to telescopes around the world, and they'll all look at this star and take follow-up detailed measurements of it so we can figure out what is going on. So that first step of detecting like a star that's doing weird behavior, we would like to automate that, because there's so many stars in these surveys that, like billions of stars, that we want something that can read through all of them and detect kind of weird behavior. Mm-hmm. So in this paper, we looked at, so the anomaly detection algorithm we used is basically take, like, I guess, the algorithm we used is it's a variational autoencoder. Mm-hmm. So variational autoencoder, you take input data, you try to compress it, and then you decompress it, and it should match the original data. Mm-hmm. Now, once you've trained this like compression decompression algorithm, what you can do is, if you compress like a new observation to this compressed space, you can look in this compressed space. Never seen any compressed variable like this. Like, this is so far from anything else I've seen before. Mm-hmm. That is basically how you do anomaly detection. So say you have, say you have a bunch of images and you compress them to two variables. You compress them to like points in a 2D space, mm-hmm. right? You have all these images and you compress each image to a dot in a 2D space. Anomaly detection will basically you have a new image, you compress it to a point in this 2D space, and it will be far away from the other points you've seen. And that tells you this is a weird input. I've never seen any input like this. So it's an anomaly. So that's the basic premise of this paper, is you train on stars you've seen before. And then when you use this in an astronomical survey, maybe you have a star, you pass it through this compression engine, and it's far away from every other point you've seen. And then you know, like, this is a weird observation. Maybe we should do follow-up studies about it.
Mm-hmm. Great. And
Yeah.
I mean,
So,
probably doesn't make sense.
Yeah, maybe it would be interesting.
Yeah, sorry? Yeah.
Oh, I was going to say, maybe that kind of approach would be interesting for the space weather thing.
Mm-hmm.
Like maybe you have observations of the sun, like the sunspots or something,
Mm-hmm.
and maybe you measure like, oh, this sunspot looks like nothing I've seen before. Maybe that's a trigger.
Yeah.
That there's going to be like a geomagnetic storm or something.
Yeah. Yeah. Indeed. Yeah. Yeah, but the input in this case could not simply be a time series. I mean, you need pictures or something.
Right.
But yeah, definitely. Yeah. And is this related? I mean, the idea of additional encoders, of anomaly detection in general. Do you know if this is related to topological data analysis somehow?
No, I don't actually know about that.
Okay. I don't know. I mean, yeah,
It's
just
a topological data analysis.
Just I don't know. I don't know either. It's just a thing I've been looking at recently, and it seems like, I mean, you have, because you said basically you have. I had this idea because you were saying you have anomaly when you have some kind of, I guess, norm in this compressed space, which is bigger than something you're looking for, and in topology data analysis, you have some kind of measure associated to homotopy, which I have no idea what it is, but basically, yeah, I don't know. Maybe they're similar. I don't know.
Yeah, I know there's a lot of different ways of doing anomaly detection. So the autoencoding strategy where you're detecting anomalies in that late space, that's definitely not the only way. There's a lot of other strategies that are really interesting. And I think many different fields are interested in this problem.
Yeah. I see. Yeah, to wrap, I mean, not to wrap this up, but okay, maybe I can cut this. Yeah, I have another question about the use of AI for reconstructing Lagrangian systems and why this is preferable to Hamiltonian formalism. You talk a lot about symmetries. How does going back to Feynman AI, how does Lagrangian neural network leverage symmetries?
Right. So the first paper by Sam Greydiness, so that his paper on Hamiltonian neural networks, that's one of my favorite papers of all time. I love that paper. It's basically, it's a way of, if you have a neural network that you're training to run a simulation, like you're learning a simulator, it's a way of enforcing energy conservation in that learned simulator. And the reason it so if you use this and you actually run a simulation with it, you'll see it conserves energy quite well. So it's kind of, you're encouraging it to be energy conservative. So if you take like a regular neural network and you just train it on some simulation, you'll see it's actually it's kind of like it introduces diffusion that wasn't in your simulation. So even if your true simulation is like energy conservative, it will actually introduce diffusion that wasn't there. And that's because neural networks always they try to be as accurate as possible, but if they don't know what to predict, they'll just go with the mean prediction. like they'll be conservative, like they'll be like conservative in their predictions, not energy conservative, but like conservative in their predictions. Like they'll make a safe choice.
Yep.
And that tends to be diffusive, which is bad if you are learning a simulator and you want it to roll out for a very long time. So the Hamiltonian paper, I guess you can't really use it for systems you don't already understand, because to use a Hamiltonian formalism, you need to know the canonical variables of your system. So in physics, you have position, and there's a thing called canonical momenta. So the momenta, it has a very specific relationship with the position coordinate. And basically, if you don't observe momenta in nature, you observe things like position and velocity and mass, but you don't observe momenta, like canonical momenta in nature. So if you don't know things about your system, you actually can't use a Hamiltonian neural network. So the Lagrangian neural network paper, it's basically built to let you use the observed variables in your system. So Lagrangians, the input to a Lagrangian is position and velocity. So the time derivative of the input coordinates. And because you're using this formalism, you can actually use this on systems you don't know about. So it gives you the same energy conservative properties, but you don't need to know the variables in the system. Like you don't need to know what the canonical momenta is. So that's why this approach we think is useful. Now, the downside is it's much more complex to evaluate. So like a Hamiltonian neural network is it's very it's linear. It's completely linear. You just take a gradient and you're done. Lagrangian neural network, you have to do a Hessian, then a matrix inverse, and then like a Jacobian of some other matrix and a matrix multiply. So it's like much more expensive, but it's the only way you can use energy conservative approaches in systems you don't know about, basically. So that's the Lagrangian neural network paper.
And this complexity comes from, because in Hamiltonian mechanics you have this symplectic form which is linear.
Yeah,
and in
exactly.
Lagrangian you have all these partials with respect to time and
so if you take the Euler-Lagrange equation, it's actually an implicit differential equation. Like it doesn't give you the acceleration. So we actually had to work out what is the explicit acceleration in this function. And that's where you get like this matrix inverse.
Right. And this is, I guess this was also a question before when you mentioned this idea of graph networks to discover physical laws. You mentioned that it's sparsity promoting because we want interpretable models. But let's say you were unlucky and you were observing something that's unrelated to the physics in which the expression is sparse. So would the approach you mentioned before work even if what you're observing is not related to something sparse? And would also Lagrangian neural network work in a case in which, let's say, the differential equation you get from a given Lagrangian is really complex?
Yeah, that's a really interesting question. So the Lagrangian mechanics, I think it would still work even if your differential equation is very sparse or very complex. The only requirement is it has to have energy conservation. So like if you have a system that actually has energy diffusion, you would have to learn a residual. Like you learn your Lagrangian neural network and then you learn like a residual that you try to make small.
Okay.
Like you learn the acceleration is the Lagrangian part and then it has like an offset.
Okay. Yeah.
But I think it would work for very complex equations. The second question about the sparsity is really interesting. So I think like if you use a model and your true equation cannot be represented sparsely inside that model, then I think you're screwed anyway. Like you can't interpret it anyway, because it needs so many dimensions to describe it. So it's going to be very hard to interpret it. So like one thing that might tell you is like, this is not the right model to use on this network. So like if it's a graph neural network and maybe you have one message passing step and the sparsity does not work, like it wants to use 100 dimensions, then maybe that tells you maybe I should use 2 message passing steps instead of 1 message passing step. Maybe you go to 2 message passing steps and now it can be sparse. So it's like, it's one indicator that maybe if your learned model it needs every single dimension, maybe it's just doing something like it's just fitting a very high polynomial fit, but it's not the actual problem. Like it's not the actual model. So maybe if you use a better structure in your model, it'll actually find a sparse solution. Like I think many cases in physics, the true model can be quite simple, and like you can always fit a very complex model to any kind of physical phenomena. Like you just keep fitting coefficients in a polynomial, you can always fit it. But it tends to not be the true model. I mean, it might be like we might find physics is just messy in general. But in many cases, there is like some simple representation that you can find, and that's where a sparsity regularization might help you.
Yep, right. And this graph network approach, I mean, I'm trying to understand how general it is with respect to, I'm coming from a dynamical systems theory perspective. So for example, is this graph network idea assuming this message to be instantaneous? So are processes Markovian? Are processes that you get out of this framework necessarily Markovian, or you can have some kind of memory, some kind of...
Yeah, so I guess like, so it is a general framework. Like you don't have to use a graph network. You could use any kind of model you want. The only requirement is you have sparse latent spaces. If you use any type of model, as long as you have a sparse latent space, you can try to approximate the relationships with symbolic regression. You don't have to use a graph network. You could use any kind of model you want. And you can use any type of input you want. So you could just like pad on the history of your variables. So it doesn't have to be Markovian. Like we chose Markovian systems, but I mean, we didn't really, because we gave it velocity, but I guess it's still Markovian, but I guess like you could always append the history of your simulation.
Right.
Yeah.
Yeah, right. And do you see potential applications? I don't know if you're familiar, kind of related to the work did on scene, the ideas of Koopman theory, in which basically you take dynamical systems, you map them to a higher dimensional space, and then you try to find a description there. Do you see potential of applicability of symbolic regression in this context?
I think the Koopman operators are really interesting. I don't know how you would use symbolic regression there, because I think in that formalism, you like, as you said, you map to a high dimensional space, whereas symbolic regression, you really want a low dimensional space.
Right.
Like low dimensional spaces are where you can find equations. Like it's hard to find a very high dimensional equation. So you always want low dimension. But I think, so I work with Steve Brunton and Nathan Cutts, and they explained their Koopman paper to me. So I think what the Koopman operator is finding is like the energy states, or it's like the energy eigenvectors of the system or something. And then you are just like updating the coefficients or something. Yeah, I don't understand it that well. But yeah, I think the Koopman operator paper is really interesting. Yeah.
Okay. Great. I mean, I hope it doesn't bother you to close the conversation with something you don't know, but I think it's probably in agreement with your philosophy. I don't know, hopefully.
Yeah.
So yeah, I mean, was really interesting.
Yeah. Thanks a lot for having me.